Alright. Okay, I'm gonna go pull out my laptop. I'm gonna check to see if you
Sure.
can see you.
Just make sure things are all going right.
First it up.
Okay, probably. It's off for the moment. Okay. So, let's see. Cool. In this area. Okay.
Yeah, feel free to, when you start the workshop, just switch tabs to turn off the lo-fi.
Turn off what? I'm
The
sorry.
lo-fi.
Oh, yeah.
Yeah. It's pretty much.
It has to go through the whole spin.
I think it's muted.
But yeah, one either way.
Oh, muted.
What? Right, okay.
Oh, no.
But that's it. That's because the cursor, I think, got moved.
Okay, it's pretty much everything you need.
Alright, I'll let you know if there's an issue. Okay. Can you all hear me? Yes. Can you hear me? Yep. Online and people, can you all hear me? It is on, yes. Yes.
I have to hold it a little bit closer.
How is it now? Is that better? All right, good. We'll just give another minute or two for any stragglers. I think it'd be a good time to start now. All right, can you all hear me? All good? All right, so I guess we can get started now then. So, hi, hello everyone. So welcome. This is the How to Win Kaggle Contests workshop. So I guess let's just get started a bit with the agenda. So we're going to be going over data types, data pre-processing and processing, model architecture, how we build an architecture, HyperParameter Optimization, regularization techniques, and deadline for this. Don't be too intimidated by those terms if you don't know them. We will be going over all of these, and I'll try to explain them in as simple of a way as possible. So, who am I? Well, I'm Ryan Aspenleiter. I am a junior computer scientist here at University of Texas at Dallas. And one fun fact about me is I can wiggle my ears. So that's that. So I guess we can jump right into it then. So with a Kaggle contest, you could be working with a number of different types of data you could be working with. So it's a number of options. So first of all, a pretty common one is just numerical data. So this is pretty simple. This is just anything that is just based purely on a number. So for instance, an example up here, I don't know how well you guys can see this, but study time in hours for each student, that could be considered numerical data because you're dealing with a raw number. Categorical data is a bit different. You have a set number of categories. So in this case, it could be singing, comedy, dancing, etc. But there's a set number of categories something can be in. And if one thing is in a certain category, it doesn't really imply it's any closer to being another category. So I guess that's one of the main differences. If you have any questions, please let me know. Either ask if you're in person or send something in the stream if you're online. Oh, actually, I'm just going to answer this now. There's a pretty relevant question. So, what exactly are Kaggle contests? I probably should have led with that. So, Kaggle contests, basically, if you haven't heard of it, Kaggle is a website where basically they can host a lot of different machine learning type competitions where you can submit outputs to from machine learning, from your machine learning model to solve a certain problem that they give. And there's leaderboards and based on how well your model is doing relative to everybody else. But Kaggle is one of those one of those places where you can really get a jump into machine learning without a whole lot of prior experience. It's a good gateway. But the actual website is Kaggle.com. There's actually an AIS Kaggle competition at the moment. I'll have more of an announcement about that at the end of the workshop. But is that a fair answer to your question? Any questions? Any further questions about that? Yes. 5, 4. Okay, I guess I'll go back to that, see if there's anything more. But going back to this, I talked about numerical data and categorical data. There's also time series data. So this is when, I guess an easy example is the stock market. That's why I have that up. But basically, it's a set of data and how it changes over time, because how data is arranged time-wise is a pretty important impact. It is a pretty big factor into how you should really interpret it. And lastly is text data. So basically, any data that has phrases, words in it, that's not really a category, but you interpret the phrase. And that's what the data actually is. There is a little bit more to it than just this, but these are the main things that you will see a lot. So next slide. So the data set that we're working with in the Kaggle competition for AIS is a data set called MNIST, which this is just a set of handwritten numbers. There's a lot of these. There's thousands and thousands of them, but these are all digits between 0 and 9, and it's kind of considered the hello world data set of machine learning, where basically it's pretty well known. It's not too hard to work with, and it's pretty clear when something is right or not. Basically, each of these digits are represented as a 28 by 28 array in CSV form, which is a little gross, but you can't always have nice things, I'm afraid. Okay, quick question from online. How much experience I need to have before joining this competition? You don't really need much experience at all. In fact, I would argue you don't need any, or maybe even this workshop should suffice, honestly. But if not, Google is always your friend, and at least for a relatively simple workshop, relatively simple competition like this one, it shouldn't be too hard. We're actually going to be supplying a template you can work with at the end of the video. Sorry, not end of the video, end of the workshop. That should basically, it will cover everything besides the actual model. So you can get right to the part that I think a lot of people find the most interesting. So does that answer your question? I'm going to assume yes until I hear otherwise. So this is the, just to clarify, this is the data set that we're going to be using for the AIS competition on Kaggle. So moving on, data processing, or I guess data pre-processing. When it comes to images, which is something you'll see a lot, there's a number of cases, but in this case, let's talk about a grayscale image. So an image that only varies between completely bright and completely dark colors. So each pixel refers to has a certain number, and that number will represent the how dark the image how dark that pixel actually is. So for example, the completely black image, a completely black pixel would have a value of, I'd say, 0, while a completely white pixel would have something like 255. Now, the computer only sees those numbers. It doesn't see this image. It just sees a lot of numbers. And it only gets more complicated if you make it a RGB image, for instance. In that case, instead of one number for each pixel, you actually have a set of 3 numbers, one for red, green, and blue components, respectively. So in that case, you actually end up with a 3-dimensional matrix. So, for instance, you would have, if you had like a regular RGB image that is like a resolution of 1920 by 1080, for a computer, it'd be 1920 by 1080 by 3, because there is a red, green, and blue sheet, respectively. But for grayscale, you only have to worry about the 1, which thankfully is what we're working with for our competition. So I guess you can talk a little bit about some of this pre-processing code. This is ripped directly from the template I'm going to be giving you all at the end of this workshop. But basically, this is what this does. At the beginning, this just imports data. So it uses, there's a couple of modules that are really common for any kind of machine learning thing, like NumPy and Pandas. You will get to know those well if you get really further into machine learning, but they're pretty simple to use, generally speaking. Pandas is nice because it can be used to, among other things, to read in a CSV file and make a data structure with that. So it takes in training data and test data. Then it does pre-processing. So when you want to work with this, we're basically giving you a number of things. We're giving you basically every value in every pixel value of the digit, as well as a desired output. So for instance, if you had an image that actually was drawn to be a 9, the desired would be a 9. And in this case, it's actually under the label. So we actually do a separation here. So Y-train, which refers to the desired output for training data, is just a train data label. So specifically the stuff under that. While X-train is all the other data. This is the stuff that these would be like the questions that you would want to give these are the questions that you'd like to give to the model to answer. And the correct answers would be the Y-train. So X-train is just everything except the answers. It'd be all the information needed, but not the answer. And then you also, something that's good for machine learning models, that you can make things a little bit easier, faster to converge, all that kind of thing, is something called normalization. So if you're wondering what that divide by 255.0 is, each of our pixels can have a value between 0 and 255, right? Our models tend to perform better when those values are actually between 0 and 1. So to get it into that range, we just do that division, and it makes things easier in the long run. We also have to reshape input data. This I'm not going to go too far into, but basically it just restructures the data structure so that it better fits with the type of learning that Keras is going to do. And then lastly, this bottom thing right here, that's just, so as I mentioned earlier, the desired output is given as a number. So for instance, if the image we want, if there's an image and it's supposed to be drawn as 9, it's given as a 9. For what we are trying to do, that is not really optimal, because let's just say there's a image that's drawn as a 5, right? And let's just say your machine guesses a 3, or the machine could guess a 4. Those are both equally wrong, but if we're only talking about numbers, then 4 is technically a better answer. So we don't like that. That's not good. So we want to convert it to categorical. So I have a little image in the corner here that kind of say what that means. But basically, for instance, if there is it converts a value to basically a list of values, which all add to 1, and they refer to basically how confident the robot should be. Sorry, not the robot. The model should be when guessing a specific thing. So, for instance, if we're going off of this example, the first option is a cat. So in that case, the cat is should be a 100% chance cat, 0% dog, 0% turtle, 0% fish. That would make sense. Now, our bot is not going to be that accurate, but that would be a metric we use for learning, because ideally we want to get as close to that as possible. But if we were to have a input like that. Questions? Nope. Any questions from people in person? Okay, I don't want to intimidate you with all this. If you do really have questions, please don't hesitate to ask. I want to make this as simple as possible, so we don't you don't get lost for anything else. This will make it as easy as possible. So I guess from there we have a train test split. So what this means, we have a training set. That set is a lot, basically everything that we got that also has a correct answer associated with it. So this could be what we actually want to do is we want to split that up into 2 sections. This is because we don't want to actually have it where it overtrains, or basically we don't want it to learn this data set so well that it can't really apply it to anywhere else. I guess a good example of this would be if you're given a study guide for an exam, and those questions, there's answers given for each of these questions. And as for your purposes of learning, you just memorize the answers that are on that study guide. Now that'd be very good for learning that study guide. But on an exam, it's not going to be exactly those questions in that order. So that'd be a very, very bad idea. We don't want it to learn this model too well. So that's part of the reason we do a train test split. There's in this code, I have it as a train and a val, or validation set. What the validation set's for is basically you can use that to kind of gauge how good the model is doing without actually impacting the learning it does. So, yeah, I guess are there any questions on that? I know I kind of rushed through that. Anything from online, anything from in person? 3, 2, 1, sold. Okay, so now we can talk about the really interesting part, model architecture. This is where neural networks, all that comes in, and the part that you'd be doing for the competition that we're running. So I guess to get started, for the simpler models that we're going to be working with, it consists of a series of layers. So basically, you're going to start with input data, and then that data is going to be going through a lot of input layers. And basically with different weights and values through all the edges and the nodes. you can end up with a prediction at the end of that. Now, the most common layer that you are going to see, because this is in basically every model, is a dense layer. So what this is, you have an input layer. So each of these values, for instance, everything that's in the input layer, each node, that could be referring to a specific piece of information about the data you're working with. So for instance, if we're talking about a model that categorizes cats and dogs, like whether something is a cat or a dog, one input layer option could be how big it is, or maybe what color it is, or something along those lines. But you go down, and then a dense layer would basically be you would have another series of nodes. This is a hidden dense layer, and every single input layer is connected to every single node in the hidden dense layer. And as you can probably guess, there's a lot of edges that could be associated with that. Each one of those could have its own weight associated with it, which will affect learning and everything else. So we can talk a bit more later about how that works, but this is the most basic version, basic layer. Any questions about dense layers? I guess how they work. All right, that's okay. Now, another layer that's pretty common for anything related to images and something that will be used in the competition is a convolutional layer. I'm not going to get into the nitty-gritty about how the math works for this because it is a little weird, but fortunately there's a lot of libraries that exist that that just is in the background. You shouldn't have to worry about it. But basically, what a convolutional layer does at the high end is it looks for patterns of a certain size. It looks for a number of patterns of a certain size in an image. Like for instance, there could be 25 different filters it could look through to find certain patterns, and it could be of a certain size, like maybe a 3x3 or a 5x5, depending on how many pixels you want to work with. And it will keep track of those. It'll keep track of basically what features it finds, and it can convert that to some data that can be worked with by other layers. It's nice because you can it uses all the data of the pixels around it. So it works well with image format. And a layer that is used a lot with that is something called a max pooling layer. Again, all the data is done, all the math's done in the background, so this is actually pretty simple if you're trying to implement it in Keras, TensorFlow, anything. But basically, a max pooling layer, what it does, as you might be able to tell from this, is that it takes the highest value from each 2x2 pixel, and it converts the whole image down to something that's just a fraction of the size it was. This way you can, because in all honesty, not every pixel in an image is important. It never will be. And if you don't end up doing these max pooling, you could end up with a model that is very cumbersome and burdened by a lot of connections, as you might have been able to guess from the dense layer. It can add a lot of connections. It can make the model worse. It can also make the model take forever. There's a number of reasons why you'd want to reduce that. So a max pooling layer is extremely nice for that. Any questions? Any questions on this? 3, 2, 1. All right. So, surprise! It's member attendance. So, the code is 7536, and if you're in person, you can just use the QR code. If you're online, you can just use the URL. Let me know once you've all done that. Otherwise, I can go back here if at the end of the workshop someone didn't catch this. Okay. Yes. Has everyone gotten at least the QR code in? Am I free to go on? Speak now, forever hold your peace. 3, 2, 1, go. Okay. So now let's talk about hyperparameter optimization. Now it's honestly, those words are a bit you don't have to use this word. So it's honestly more complicated. Not as complicated as it looks. Basically, what a hyperparameter is, it's any variable that's used in your model that controls how the learning process works. So some really simple examples could be learning rate, or basically how much any particular run of the model actually, how much it'll actually change its weights based on what it learns. So if you have a really high learning rate, it will converge really quickly, but it might actually get a bad answer because it could jump over correct answers. There's also batch size, and there's epochs, basically, which determines how long the training is, or for the case of batch size, it could just be how often you want to update the weights in the model. But these are all little things that can influence how well the model actually runs, and it's important to figure out good choices for that because they can dramatically affect how well your model actually runs. And for that segue, how do we set these parameters? Because it's actually it can vary a lot between each type of data set you're working with in any kind of model. So there's not really any obvious intuition as to what's best at first. So there's really two options. Option one, this is just theory or just gut feeling. This you can just think, okay, I think this certain number would work well. Or if you just want to do a plug and chug, try a lot of different options and kind of just see where things go. And this is the one that most people use, and it's fine. It works. It's good. The other option is metaparameter optimization. So there's actually some things available through the Keras library what they can be used for is they have various tuning functionality. So they can run through a number of parameter options to try to find the best one or something that's pretty good. And this can make the process easier, but it also can be weird if you don't know what you're doing. That's why gut feeling is usually can be adequate if we're not working at a really high level, like very challenging competitions. But as I mentioned before, tuning by hand is pretty good. You can just fiddle with the parameters to get what you want, and it's the most common type of hyperparameter optimization. Don't be afraid to change everything in your model in terms of your hyperparameters. It can be kind of weird how they interact sometimes, and if you ever feel stuck, don't feel bad if you want to change every single value to something. Or you can mess with this a lot. It does affect how things perform very dramatically. So now, regularization. I kind of touched on this idea before, but basically what regularization is, it's basically, it's a way to prevent underfitting and overfitting. And by that, if a model doesn't really have the capacity to learn as much as it can, if it doesn't have enough data to work with, not enough time, it won't learn. I mean, that part's pretty intuitive. And that would happen, like, for example, if you're in an exam, you have a study guide, and that study guide has like 3 questions or maybe like 10% of the type of content you would expect. That's not really enough to learn everything if you're just using that to learn, which you shouldn't. But overfitting, opposite side of that, is if it learns the model so well that it can't really generalize the ideas anywhere else. So this is, I guess, going back to my example before about, say, a study guide where you have a lot of questions and they have all the answers, and you can just memorize the answer for every single one of those questions. But the actual exam might have the questions that they can be similar, but they won't be exactly the same. And because you're just memorizing the answers, you're not going to be doing very well. You can't generalize. So that's why it's important to find an ideal fit somewhere in between. And there's a few different approaches for that. We're going to be going over a couple of them. So first of all, I mentioned all that. First of all, dropout. So this is actually another type of layer I didn't mention before, but it's very useful now. Basically, what a dropout layer does, it will randomly set some of the nodes or some of their activations to be 0. So basically, you can treat them as though they don't exist because they won't have any impact on the neural network. You'll do this randomly to some proportion of the layers. So for instance, in that case, what you do this way is you prevent the model from relying too much on specific nodes. Because this dropout happens randomly with every so often. And when you do it like this, as I mentioned before, you don't end up with a node that becomes too dependent, that becomes too important, and it could end up with overfitting otherwise. So that's why this is good. And it also reduces the amount of connections you have to work with, which is also nice. So if there's another example, it could be different the next time. If it was the same every time, it won't be much of a benefit. Second option is early stopping. So there's also the idea where I'll just show you, let's just say you have a machine that's learning like this. You want to minimize loss. There's testing and there's training. The testing is just what you use to validate how well your machine is doing without using the testing data specifically for learning. This is just the test, but it's not the study guide. And as you can see, those losses both go down over time. However, when your training data tries to get really close to a very, very small loss, that'll result in generalization being very poor. So test data loss actually starts to increase after a certain point. And if you want an optimal model, you probably want to end up right around here. You want to end up where the testing data is minimum. The testing data loss is minimized. So we have to figure out the optimal point to stop training before loss starts to get too bad on the testing side. I'm gonna stop it right there. If you don't do it, if you don't give it enough time to really learn its data, you'll be underfitting. Otherwise, you'll be overfitting, as I explained earlier. So there's a few options. Let me just go back real quick. Pardon me. So there's a few options. One, you can just stop it manually. If you observe that the validation data loss is actually starting to get too high, or I guess another way of saying it is the accuracy of your model starts to get a lot worse, kind of just starts to happen. And you don't want that, so you can stop it early. Otherwise, there's various mechanisms, like for instance, you can make learning rates drop over time so that it won't change too much. It won't learn as much as time progresses. So this overfitting issue is mitigated to some extent. And there's a number of other approaches, but this is something that you have to keep track of. Training for 1,000 years on a data set isn't going to necessarily make a better model. In fact, it'll probably be worse than one that doesn't train that long, because it's going to know the data it's working with very, very, very well, but it won't know how to apply that to anything else. So that's the purposes of overfitting. So I know I kind of rushed for all that. Weren't really any questions before. Is there any questions about anything? I can go any of this in a lot more detail. Any clarity issues? Oh, yeah.
So when you're stopping the model, or what would that look like when you're training it? Is it just like you just revert to when the model was at that stage, or?
So I guess there's a number of ways you can do that. So I guess one way of trying it is just messing with the number of epochs you're working with. So I wasn't super clear about what this was before, but basically what an epoch is, it's how much one epoch is when the model goes over the entire training data set once. And what you could just do is mess with that over time. So for instance, if you run it with epochs, let's say there's 100 epochs, and you notice when you're running it that at about epoch 50, the validation loss isn't really getting any better, or maybe it's getting worse. What you can do at that point is maybe if you really want, you can just run it again at 50 per se. Or maybe I'm not quite sure how the mechanism would be set up in Keras, but you could probably, I wouldn't recommend manually stopping it, but you can kind of experiment. Does that answer your question? I'm sorry. Okay. Any other questions? All right, nothing online. All right, 3, 2, 1, go. So, if any of you have been following the Discord recently, you might know about a Kaggle AIS competition that we were having set up. Now, I mentioned that before at the beginning. We'd be working with the MNIST dataset, which is basically just the dates. That was originally due tonight, but we are actually moving out a little bit, so people would have access to this workshop to get a little extra information. So this can actually be Monday, 8 p.m. And I have a link right here that is to a template Kaggle dataset, template Kaggle workshop. I'm sorry, not a workshop, a notebook. This is something that I made that basically takes care of everything besides the model. You can obviously mess with this stuff outside of it as well, but the model is what you should probably be focusing on, at least at the beginning. And this would remove too much hassle when it comes to pre-processing or getting the data in a nice form. Yeah, I guess one final plug. So AIS is having a BOBA fundraiser, and if you want to hang out, support, it's to be in Union a week from now, 11 to 3 p.m. And if you just want to check us out, hang out, have boba, highly recommend. It benefits us. It helps us a lot. Helps you guys a lot. We can keep doing these. And yeah, cool. Okay, is this a team-based or individual competition? So you could do either. So you could be individual, but you can also have a team where basically, I don't know if we set a hard cap, but I wouldn't make it a particularly large team, like probably no more than say 3 or 4 people. But 4. Okay. So the max would be 4 people. But basically, yeah, it's team-based, but it not like you have to be in a team if you really don't want to, but you could benefit. You can benefit from your team. They can benefit from you if you guys want to make a better model. But it is up to you, and if you don't want to make a team, it's entirely your choice. If you do want to make a team, highly recommend that. So, any other questions about the competition, Kaggle, anything I mentioned? Any questions? Yeah.
Can you go back to the membership slide?
Sure, give me a moment. There you go. Is that good?
Yeah.
All right. Then if there are no questions, I guess we can end a little bit early. If anyone wants to come up and ask me questions directly without having to say it out loud, you're free to come up here since I'm done with this. And if you have any questions, let me know. I'm on Discord. Any of the officers are also on Discord, and we can help you out. There's a lot of stuff we can do to help. And that'd be it. Thank you. Oh, you wanted to, sorry. Let me just go back to, okay. I guess it's done.
Good job.
It's quiet.
Okay, this. And do you want to stick around for the whole?
Like another few minutes or so, see if there's anyone.
Excuse me. Can I ask how exactly you going to update the mod for the code CAD competition that can do a CSV file?
So, okay. So first of all, I wasn't super clear on this, but basically, what you actually submit to Kaggle is your predictions, not your model.
Yeah.
But basically, that's actually part of the template. I have it where when it does the predictions, it'll actually output the CSV file on its own. If you want to look into that more, you can look at the code. Otherwise, it's not a number of options. But that should make sense. Yeah, if you just want to start out, you can make it has everything minus the model, so you just add the model and it should work, provided the model is not so crazy. But you can also mess with that. Yeah, there's two versions. But short answer is that.
Okay, awesome. Thank you.
Direction. So one is the template. Is that posted outside?
I can put that in the issue.
Also, I think earlier in the workshop you mentioned something about resizing.
Oh, you're reshaping the data.
Yeah. What would be the numbers?
Sure. So, first I'm not basically, it's like you're reducing the dimension a little bit, but it's so the 20 is pretty simple. Those are just the 28. The images we're working with are 28 by 28. So that part makes sense.
Yeah.
And because it's grayscale, it only has one color dimension.
Yeah.
It's just how dark it is. I forget what the negative one is, if I'm going to be perfectly honest, but I believe that's just a way that you can. It takes care of some of the dimensionality. If you're curious, you can always just Google the documentation.
Yeah.
But that's my explanation.
So it's kind of similar to when you earlier when you showed that one slide about max sizing, where you were just thinking like 2 by 2s and thinking like the greatest value. Is that similar, or is that?
Okay, so it's sort of different. I guess let me go over the reshaping again. So the data that you're given, it's a CSV file. That's dumb. It's very dumb. Like you're given, it gives you the value of every single pixel in a straight line. That's weird. I know.
Straight lines.
Like for instance, like in the CSV file, you're going to be given each line, each row is going to be 28 square. Number of values. It's just flat. With each column referring to each pixel. We don't want that. We want it to be in a 2 by 2. We want it to be in like the grid, like actually a 2 by 2 by 1, I guess. We want it to be like that. So that's part of where the reshaping comes in. We have it like that, and then when it's in that kind of dimensionality, then the convolutional layer can actually. Okay. Did that help? And then I guess for max point. That's something you'd use like after a convolutional layer. So if you want to use that, you can basically take out it takes out patterns that aren't showing up often or taking space. And they can make it where you want to focus on the patterns that are.
So there's a kind of particular order to when you're like making the data fit, or when you're preparing the data, it's like a set of like there's kind of almost an order to it.
There is some of it, yeah. But I will say the layers are completely separate from the process. Well, not separate. Like the inputs have to make sense.
Yeah.
But other than that, that's what preprocessing does. Like because our model is working with a 28 by 28 by 1 value, we need to change the data so it fits. But that's basically. I'm sorry. Was that a good answer?
Sorry.
Again, sorry.
Also, with the CSV file, you said everything was read in a line. So does that mean like